Hi everyone, I'm Mingcong from iPads at Shanghai Jiao University. So I'm so excited to present our work titled Colocating ML Inference and Training with Fast GPU Memory Handover. So in this work, we built a new system, SIRIUS, to improve the GPU utilization in machine learning workloads. So let's start with a common problem in machine learning services, the GPU underutilization. Inference workloads are known to be fluctuating and bursty to meet the service quality goals, companies often have to provision GPUs for the peak workload, so everything can run smoothly at all times. However, most of the time, the workload is not at its peak. This leads to a significant issue. Our expensive and powerful GPUs are sitting idle, wasting valuable computing resources. This over-provisioning is inefficient and costly. So how can we solve this? In this work, we propose the approach of colocation. We propose running latency-sensitive ML inference services and throughput-intensive training tasks on the same GPUs simultaneously. So by prioritizing the critical inference service, we allow the long-running training task to saturate the GPU's remaining capacity. Our goal is simple: to achieve maximum GPU utilization without violating the strict performance requirements of our inference services. But this brings us a major challenge. Both inference and training are very memory heavy. An inference service might need to hold numerous models in memory, and a training task has its own large memory footprint for its states. The problem is here. The GPU often doesn't have enough memory to hold both at the same time. So let's look at how this problem has been tackled before. One common method is static memory partition. Here, we divide the GPU memory and assign a fixed portion to the inference service and the rest to the training task. This approach is simple, but the problem is that it cannot adapt to the changing workload. So under a high load, there might be enough memory for the inference service, which can hurt the service quality. And under a low load, the memory allocated to the inference service is wasted. So this static approach forces a compromise that hurts both the utilization of GPU and the performance of the inference service. A second approach is dynamic memory swap, which can be achieved in two ways. The first way is through a software task switch. When an inference request arrives, the system stops the training task and swaps its data out of the GPU memory. While this sounds adaptable, it introduces a massive overhead from context switching. The time it takes to load a new model causes a long resource time for an inference request. And if inference requests arrive frequently, the training task can get starved. The second way is by using the hardware unified memory. This feature allows the GPU to see the host main memory as part of its own address space. However, when the GPU needs data that isn't in its local memory, it has to fetch it from the host over the much slower PCIe bus, and this also creates substantial memory swapping traffic that degrades the performance. So we can see that both of these dynamic swapping methods compromise the performance of both the tasks. So in this work, we propose a new approach. We call it dynamic memory transfer. Instead of swapping memory out of the GPU entirely, we transfer it directly between the training and inference tasks. Here is how it works. The inference service is always prioritized. When a new inference request arrives, our system dynamically scales down the memory allocated to the training task and reassigns it to the inference service. And once the inference work is complete, the memory is then transferred back to the training task. This allows us to constantly adapt to the fluctuating demands of the inference workload. But the fundamental problem we had to solve is this. How does the training task continue its execution after part of its memory has been taken away? Our key insight is to use the training elasticity. Modern deep learning models are trained iteratively using small sets of data called mini batches. A significant portion of the GPU memory used during the training is for storing the intermediate data for this mini batch, and the size of this memory is directly proportional to the size of the mini batch size. So by dynamically changing the mini batch size, we can control the memory footprint of the training task. When the inference task needs more memory, we can reduce the training batch size and free up its memory. And when the inference workload is low, we can conversely increase the batch size to speed up training. Note that changing the mini batch size does not affect the model's convergence because a well-known technique called gradient accumulation can be used here. So this is a key insight that allows us to transfer memory back and forth between the two tasks and keep the training task running continuously. So with this approach, we built SIRIUS, a system designed for efficient ML inference and training colocation. At a high level, SIRIUS has two main parts: a custom inference engine and an extension for the PyTorch training framework. The inference engine manages the incoming inference requests and determines how much memory is needed. When it needs more memory, it sends a required request to our PyTorch extension. The extension then changes training batch size to free up that memory. Conversely, when the inference task releases memory, the engine sends a release notification so the training task can reuse that memory. While using training elasticity for dynamic memory transfer seems promising, it introduces a critical risk. It may still hurt inference service quality if it cannot transfer memory quickly enough when a new request arrives. The speed of the memory handover is the most critical factor for this approach to be practical. Consider a naive approach, including waiting for the current batch to complete, releasing the memory used by it, allocating memory to the inference service, and loading the inference model. This can take hundreds of milliseconds, which would violate a typical inference SLO of less than 100 milliseconds. This brings us to our key challenge. We must achieve a fast memory handover. To tackle this challenge, we propose three key techniques. Each one is designed to optimize one part of the memory handover process. Our first and most critical technique is releasing the training task's memory almost instantly. A key observation makes this possible. A training batch has two distinct phases. The first is gradient computation, which takes up over 90% of the execution time, but doesn't actually change the model's parameter state. The second is model update, which is atomic but extremely short, usually less than 10 milliseconds. This observation leads to our approach. When the inference service needs more memory, if the training task is during its gradient computation phase, we simply interrupt it and discard the current in-progress batch. And if it is during the model update phase, we just wait for it to complete. This optimization allows us to free up the memory used by the training batch in just a few milliseconds. But how do we discard a running batch? The challenge here is that many operators might already be running on the GPU. Our solution is to buffer the training operators in a software queue on the CPU side before sending them to the GPU. This limits the number of operators that are actually in flight on the GPU at any given moment. When a memory request comes, we stop adding new operators to the queue and wait for the few in-flight ones to finish, and then simply clear the rest from the queue. This gives us a mechanism to discard the batch quickly and safely. Second, instead of letting each task manage its own memory, which can be slow, we create a central shared GPU memory pool. It can avoid the overhead of default GPU memory allocator in frameworks like PyTorch and NVIDIA's runtime. We also ensure this process is safe to prevent any data corruption between the two tasks. Our paper details how we integrated this custom memory pool with PyTorch. Our third technique addresses the problem of memory thrashing. With highly dynamic workloads, memory can be frequently reallocated back and forth between two tasks. This is not efficient as it causes many cold starts for inference requests and frequently interrupts the training task. So to prevent this, we propose an SLO-aware allocation strategy. We reserve a small amount of memory to cache idle inference models for a short period. This way, if a request for a recently used model comes in, we don't need to perform a full memory handover. And we control the granularity of memory reallocation using a watermark system. Instead of giving memory back to the training task immediately, we wait until a certain amount of free memory, or watermark, has accumulated. And our paper details how to use a queuing theory model to find the optimal watermark size that balances the performance and efficiency. And our paper also covers several advanced topics that we won't have time to discuss in detail today. These include how SIRIUS handles multiple GPUs, how to collocate large language models, and how to prevent interference on the GPU's computation cores. I encourage you to read our paper for more information on these topics. Now let's move on to our evaluation. We compare SIRIUS against several baselines, 2 configurations of static partitioning, and task switching, and NVIDIA's unified memory. The evaluated workloads included generated and real-world traces. So let's look at the results on a single GPU. The top graph shows inference SLO compliance. It means how well we meet our performance targets for the inference service. And in this experiment, we set the SLO of each request to 4 times of its model's standalone inference time. And the bottom graph shows training throughput. First, focus on the static partitioning approach. With a 50-50 split, it gets a relatively high training throughput, but has very poor SLO compliance, averaging only 40%. And to fix this, we can give more memory to the inference service, as in the approach of SP75. This can improve SLO compliance, but at a huge cost. The training throughput drops by almost 3 times. This shows that the static partitioning approach forces a trade-off between inference quality and training throughput. Now let's look at the swap-based methods, task switching and unified memory. As you can see, both of them perform poorly. Their SLO compliance is extremely low, around 22% for task switching and just 2% for unified memory. Their training throughput is also significantly lower than expected. This is because the memory swapping overhead through the slower PCIe is extremely high and bottlenecked by the PCIe bus. Finally, let's look at SIRIUS. Across all workloads, SIRIUS consistently achieves nearly 100% SLO compliance. This is very close to the performance of running inference service by itself. Overall, compared to all other methods, SIRIUS improves SLO compliance by an average of 57% and improves training throughput by an average of 2.2 times. This shows that SIRIUS can eliminate the performance trade-offs, achieving both high-quality inference and efficient training. And this performance improvement is powered by our fast memory handover mechanism. The naive approach, which waits for the training batch to finish before reallocating memory, takes over 250 milliseconds. This is far too slow for an inference task. In contrast, SIRIUS completes the entire memory handover in under 25 milliseconds. SIRIUS also works well on multiple GPUs. In our 4 GPU experiments, SIRIUS again showed significant improvements in both inference performance and training throughput compared to other methods. And in conclusion, we introduced SIRIUS, a system that uses training elasticity to share GPU memory efficiently. SIRIUS allows us to fully use expensive GPU resources without sacrificing the performance of inference services. Our code is open source on GitHub, and thank you for your attention. I'm happy to answer any questions.